So, good morning, everybody. So, let's go to our first speaker today, which is Barry Sanders. Barry, you have 35 minutes, okay? I will tell you 5 minutes before for discussion. Good.
Okay. So you can hear and see me okay? Thanks for the invitation. I wish I could be there in person. It looks like a great event, but I'm glad to be able to speak virtually. And the talk that I give will connect with some of the people in the audience, I expect. I've written a long title, so I kind of think that the importance of your work is proportional to the length of the title. So I wrote a very long title to make it sound important. The talk I'm going to give is on kittens, cats, compasses, and combs, superposing coherent states for quantum sensing, quantum communication, quantum computing, and quantum fun. Most of the talk will give you perspective and history of this topic of superposing coherent states. And the last quarter of the talk will be on some new work that appears in the archive paper. You can see below the that reference on macroscopic Schrödinger cat states on a nucleus. Okay, now, sorry, I gotta change the slide. Okay, so first of all, just a bit of history on cats and coherent states. So here at the top left, I use short DOI. So DOI.org is the site that registers all digital objects, gives it an identification number, and it runs a hash service that's short for that. So basically, if you see 10/ and then 6 alphanumeric characters, you can type that into DOI.org and look up the original reference. That's Schrödinger's paper where he talks about the Schrödinger cat state, what we now think of as the Schrödinger cat state. And I'm not going to go into the story, essentially that there's a radioactive nuclear decay that gets entangled with whether the cat's alive or dead. And so the concept that we take away from that is that Schrödinger's cat states refer to the idea that it's a superposition of two classical states. And by classical, I mean coherent states are seen to be the most classical of the quantum states. They follow classical dynamics, they're minimum uncertainty states, and they're not completely orthogonal, but they can be put far enough, there could be a sufficient distance between them that the overlap between the two states is negligible. We identify Schrödinger's cat paradox with the idea of superposing two coherent states. And the idea of coherent states, we often identify with Glauber, who won a Nobel Prize for his work on coherent states. I have his 1963 work captured below with the short DOI. But on the upper right, that's Schrödinger's early paper where he solves wave packet dynamics in a harmonic oscillator. That's a Gaussian wave packet whose center of mass follows the classical motion of the oscillator, and it's a non-dispersing wave packet. And so Schrödinger himself introduced the coherent state, and then it was Glauber later who recognized that representation was very useful for quantum optics. Okay, so that's the idea of the cats and coherent states. So this paper from 1974, in my mind, and of course, we're celebrating Victor Dodonov's career here, and I think one or two of the other authors could be present. They had a paper in 1974. In my understanding, this is the first paper that introduces the cat state, a superposition of two coherent states. This paper is called Even and Odd Coherent States, and you can see it's rather mathematical. Down on the lower left, you can see that it talks about U11 and UN1, the unitary, non-compact unitary groups. And on the right, you can see there's a superposition of Glauber displacement operators. In equation 2.11, ket alpha plus and ket alpha minus are two different superpositions. Those are two different superpositions of coherent states. And so this paper in mathematical context introduced the idea of what are now cat states. Years later, and I'm not sure if they knew about that earlier work. So what happened was there was a paper that came out by, not shown here, by Jared Milburn in Physical Review A, I think in around 1985 or 6. And in that paper, he studied what he called the dynamics of the anharmonic oscillator, now thought of as the nonlinear oscillator. And he showed that under some kind of a nonlinear coherent evolution, a coherent state would evolve into a superposition, would evolve according to a nonlinear dynamic. Basically, the coherent state would shear into what was then called, not long after, was called a banana state, and that eventually it creates this cat state that you can see spinning around. It appears in Milburn's paper, but he doesn't actually discuss the state. And I was a postdoc with him at the time, so I remember this history well. Yerke and Stoller were aware of that in the paper, and they decided to explore fully that cat state, a superposition of two coherent states. So in a rather famous and celebrated paper from 1986, they showed that a nonlinear evolution, so the Hamiltonian of the harmonic oscillator goes as the number operator. This is a Hamiltonian that's a sum of coefficient times number operator plus another coefficient times the square of the number operator. And then they show in their paper that, that they get a cat state. In the lower right, you can see with respect to, say, position, or quadrature, you have a sum of two Gaussian states. And in the conjugate canonical quadrature, say momentum, you get a single Gaussian with a modulation inside that goes at, say, the one photon limit. It's sometimes called the Planck scale. And they then study some decoherence in the system, but they point out that there's a cat state, and then through positional momentum measurements or optically homodyne measurement, that we're able to see the complementarity, that there's the mixture of two Gaussians in one quadrature and an interference effect in the other. And you can see on the left, and this is a little bit important, is a phase-space representation. So there's two coherent states as yellow blobs with red in the middle. And then in between, you can see, well, first you see it's rotating. So because of the number operator term, there's a rotation, and the number operator squared led to the evolution of the cat state. There's a dynamic that means that these cat states aren't stationary. So in experiments related to these, one has to bear in mind this, whether the cat state sits still in phase space or rotates. What's interesting between those two coherent states is the interference fringes, and you can see a set of lines that have interference orthogonal to the axis that connects the two Gaussian blobs. And the spacing is, again, what some people call the Planck scale. Note that these features aren't directly observable. So you can see on the right of the green square and below the green square, those are the results of ideal homodyne measurements that show how we interpolate between two side-by-side Gaussians and one Gaussian with some sort of modulation. And so they're features in phase space, but they're not directly observable. We always have to remember that there's some kind of a marginal distribution corresponding to measurement that we then infer. We might be able to see all this through a tomography process, though. Okay, now the cat state idea, after it came out, experiments followed. So the first paper I know of that claims to see cat states is actually a kitten state paper. This came out in Science in 2006 by the group of Philippe Grangier in Paris. And they call it a kitten because the cat state has a superposition of two coherent states with negligible overlap. They call this a kitten state because the two coherent states have non-negligible overlap. You can see in the abstract that the kitten is generated by subtracting one photon from a squeezed vacuum beam. So nowadays, I don't think we would really think of this as a cat state, but it gives, the reason they refer to it as kitten states is because the fidelity between the state that they get and the kitten state is very high. So it was an important step towards making cat states, but it's not the method we now use. There was a really remarkable result in 2013 in Science by the group of Devoret and Sholkoff at Yale University. And you can see from the title, deterministically encoding quantum information using 100 photon Schrödinger cat states. Now remember that if there's 100 photons, then the amplitude of the coherent state is the square root. So the square root of 100 is 10. So by the title, it's a superposition of a coherent state with amplitude 10 and a coherent state with amplitude minus 10. And the width of the state is order 1, and these are Gaussian. So these are really very much almost orthogonal. So it's a wonderful cat state result. They say in the abstract it's up to 111 photons. So it's even, the result is even better than what the title suggests. And they do this in a superconducting system using a dispersive interaction. And on the lower right, they introduce a quantum circuit diagram to explain how it works, to help aid understanding how they develop these states. One reason the circuit diagram is there is for quantum optics people, it's not so easy immediately to know how the superconducting system works, and these circuit diagrams help us to follow those kinds of steps. So the circuit diagrams are very useful in studying these superconducting system realizations. Sometime later, years ago, I got interested in the idea of whether there's the superposition of coherent states with 2 degrees of freedom. So instead of a coherent state of an oscillator, think of a coherent state of 2 oscillators, and then make that a superposition with a coherent state of 2 oscillators. I wrote this up probably early 1990s, but after I wrote it up, I started to understand better the history. And so these entangled coherent states are superpositions of 2 or more mode coherent states. And then I did this study going back in time, how far back in time these things occurred. And it goes back to, so the first paper I found with a superposition of pairs of coherent states was by Aharonov and Susskind in 1967. So back in 2012, I had a paper on 45 years of history of entangled coherent states. So this gives a very good idea of extending. This paper gives a very good review, I think, of the time on a very complete history of studies of superpositions of pair coherent states. It's interesting that the superposition of pair coherent states, of 2 coherent states, appeared in 1967, and then it's the even and odd coherent states that appeared in 1974. So there's an interesting historical anomaly here. So when I studied these entangled coherent states and started learning what people did before I did it, it was at the time when I would give a talk on it, this is in the early 1990s, people thought it was science fiction, and I thought it was science fiction. But this paper, it also came out from the group of Devereux and Sholkoff at Yale University. Not long after the paper I just showed you before, this one is 2013. So by 2016, they were able to make, they have 2 boxes. The title says, A Schrodinger Cat Living in 2 Boxes. So they make a coherent state in 2 cavities. So it's a product of 2 coherent states, and they make it as a superposition of a product of 2 different coherent states that are maximally out of phase. You can see here that they talk about the 2-mode coherent state, and down here they say known as the entangled coherent states. So in 2016, the idea of a superposition of a product of coherent states was actually realized in the lab. And again, just as with the other case, really compellingly, 100 Hilbert space exceeding 100 dimensions. And as before, they explained the way that the system works with their transbonds in terms of a circuit diagram. And you can see that they do tomography of the state to be able to check that they get the state that they promise. So the entangled coherent states were realized experimentally in 2016. Now I'm going to get to the uses of these things. It came out in 1999. I mentioned Milburn's name before with his paper revealing but not discussing the realization of cat states through a nonlinear evolution. And Milburn, along with Paul Cochrane, who was a student at the time, Bill Monroe, I think was a postdoc then, they had a paper out in 1999, and they said, if we can make cat states, then we can use these for a bosonic code, in this case for amplitude damping. This is the first paper that introduces the term bosonic code, and one of the promising directions in optical quantum computing these days are bosonic codes. So it came up in this paper. They showed how they would how they could protect against basically an error correction paper using Schrödinger cat state superposition of two coherent states. You can see in the lower paper, not long after, I talked to Bill Monroe and Jared Milburn, and we talked about the 2-qubit gate. So for quantum computing, you want 1 qubit and 2-qubit gates. And so we worked together on entangled coherent states, and we were able to then fully develop both single and 2-qubit gates for ion traps. And then again, these ideas live on in bosonic codes for quantum computing. Not long after this, there was some work that came out in 2001 by Gottesman, Kitef, and Preskill, and they consider a extension of a cat state. So let me explain what went on. There was a paper by Canilla, Flam, and Milburn in the same year, a few months earlier, that appeared in Nature. And in that paper, they proposed universal quantum computing with photons. And in that case, the qubit was a photon in a superposition of two paths. In this work by Gill, they said they thought about what's called the continuous variable setting. They didn't like it because they can't do error correction. And they said, what if we could do something and it's like a cat state? You can see in the right, let me just count them. So it's 1, 2, 3, 4, 5, 6, 7, 8. So in this picture, it's a superposition of 9. It could be 9 coherent states, 9 squeeze states, but it's 9 Gaussian states under a Gaussian envelope. But ideally, the way they think about this is what I call a comb state. Most people call it GKP state. I call it a comb state. And so here, think of the ket 0 bar as being an encoding of the logical 0. And it's a superposition of infinitely squeezed states, infinitely many of them, spaced apart by 2 alpha. And so they show that this subject to, there's a little bit of carelessness, deliberate carelessness for simplicity on playing with infinities. So if you have infinitely many, infinitely squeezed state, there's problems, including the 2 infinities don't commute, but we'll push that aside. So this comb is the logical 0. Displace it so that this comb has the tooth halfway between the teeth of the other comb, and this is the logical 1. And then they say, if we then go to the dual basis, the logical 0 plus logical 1 or minus, so they develop this whole code, and then they say realistically, we can't make an infinitely long comb with infinitesimal teeth, so that's when they point out this work. Generally, it's thought that if we can make these things with 7 Gaussian states surviving in this Gaussian envelope, that might be enough to do quantum computing subject to error correction. This is actually a very important direction in some of the optical quantum computing companies where they're trying to make these things. And the relevance to this talk is that we've gone to a superposition of multiple coherent states, and this is the comb part of the title. So there are make these comb states and use them for quantum computing. So that's a quantum computing application. You can see here that superpositions of coherent states, cat states, are also important for quantum communication. In this abstract here, it says, talks about cat states, if they could be controlled, allowing for their quantum superpositions, running your cat state, then we could do coherent state quantum computing, quantum metrology, and a quantum repeater. And they say we demonstrate a basic coherent state quantum computing protocol where they use this as an entanglement resource. And they go down here to say multi-area phase shift key coherent states could be used in optical quantum communication. And essentially, this is a teleamplification. So it's a kind of teleportation protocol to be used for quantum communication. So the idea of using cat states for this purpose is also considered an important direction in using cat states for quantum communication. I want to talk too about the metrology direction. So there was work that came out in the year 2001, and this is by Wojtek Zurek, who it's a paper in Nature, 2001, and it's a very nice read and very simple to read. So it's kind of if you want to read it, it's not hard to go through the math, and it gives you a lot of insight. And essentially, what Zurek is saying is the following. So he's saying instead of a cat state, let's make a compass state. And why is it a compass state? Because the yellow blob on the top is in the north. The yellow blob on the bottom is in the south. The one on the right is in the east. The one on the left is the west. So he calls it a compass state because it's a superposition of 4 coherent states, which in phase space are at the north, south, east, and west corners. Then in between the nearest pairs, like the north and the west, you can see these parallel lines that we saw in the slide about the Yorke-Stoller result. And the idea is that these ellipses that form are at Planck scale. This is the fundamental resolution that we expect when we superpose coherent states. But he says, now look at the middle. So don't look at the lines that show interference between nearest neighbors, but what about the region of phase space where all 4 coherent states interfere? And then you can see here that it's just a bunch of little blobs, and the sizes of those little blobs are smaller than an argument that was often brought up. Space has a limited resolution. You can see in the abstract on the left that Zurek justifies the interest in that blob in the middle. He says about Heisenberg's uncertainty principle gives a limit of resolution of reduced Planck's constant h bar over 2. Then he says it's usually taken to imply that phase space structures associated with Planck scales do not exist. And then he says they do exist. And he shows that the phase space has what he says here, develops a spotty structure on the sub-Planck scale. A is h bar squared over A. So capital A refers to the separation of the coherent states, and the more they're separated, the finer the scale. Remember, I said earlier that phase space features are not directly observable. So we always have to be careful about these things because we need to figure out not just what it looks like in phase space, but how to observe these things and whether we can resolve it. Okay, but that was Zurek's argument for compass states, and it's a generalization of the cat state. Okay, now I'll go in another direction, which is the idea of generalizing it mathematically. We saw hints of that in the work by Dodonov et al. With the U11 discussion. So there was some work that came out early on by Arecki, Kittens, Clowder, and others on what were called atomic coherent states that used SU2. And then it was Perelomov in Moscow who recognized that the idea of coherent states could be generalized. Other people generalized by like Barut and Girardel and others, but Perelomov's generalization really captured the idea of classical motion. You know, that if we have some Lie group and we construct a coherent state for that, we can generalize the idea of a minimum uncertainty state and following the clock. And so in this paper in Communications and Mathematical Physics, he goes through the principles, develops for SU2 and SU11 and SO3, well, SU2 and SU11, and then he wrote a whole book that covers other groups. The book is excellent. Back when I was a postdoc, I studied it very carefully and used that a lot for my own work. And then certainly for me, influenced by Perelomov's work and these cat state ideas, back in 1989, I started playing around with the spin system using this Perelomov and this Arecki, Kittens et al. Work, and using Milburn's idea of a nonlinear evolution. So I applied it to spin systems. And then you can see this is a stereographic projection of the sphere that represents, it's kind of a phase-based representation of angular momentum. And then there's the nonlinear evolution, in this case, a JZ squared. It evolves, the phase space starts to show some ripples. And then down here, there starts to be a superposition of 2 coherent states, SU2 coherent states on the east and the west. So back then I was starting to look at these superposition states, and I worked with others. So I did some work with Wang Xiaoguang and Han Xiaohua. It's back in the year 2000, and we started to say, what if we did entangled coherent states? So I went kind of crazy then and thought, okay, I'm going to start looking at all these different cat states for all these different groups. And we went further. This was the SU3 coherent state, but this turned out to be useful for metrology. There was some work that came out in 1996 by Bollinger et al. Out of Colorado and Texas. And essentially they said, if we could make an ion trap where it's a superposition of all ground state with all excited state, we could do a better metrology thing. We can understand the physics from Dickey's work in 1954 that led to superradiance theory. Mathematically, when you understand the permutation invariance of the state, this is just a cat state for spin. So the idea of the cat state leads to the metrological advantage. And so cat states could and are turning out to be useful for trying to get Heisenberg limited resolution for things like atomic clocks. Then again, doing the group, I realize I'm running out of time. So generalizing the group theory for compass states. I've done some work recently with my former student named Akhtar and some groups, one at Zhejiang Normal University in China, another one at Shanghai Jiaotong University in China. And we've been studying the Zurich idea of compass states, but using more generalized groups to get a better feeling for what's observable and what are the metrological elements. Okay, I'm going to finish with my recent work. So this is in the archive paper that was on the front slide, came out in April. And so going back to this idea of a cat state on a spin system, I'm working with an experimental group. I'll tell you more in a moment. And we want to find a way to do a superposition of a high spin nucleus. So the high spin nucleus, I represents the irrep, the spin number for this, and we would have the nucleus spinning one way or the other way, put it in a superposition. So if we can get a high spin nucleus and make it in a superposition of spinning clockwise and counterclockwise, then I'm going to claim that we have made a cat state. And the idea, this is the phase-based representation, how we plan to do it. This is for a spin 7-half system. You can see the evolution. And then here under our evolution, it forms a cat. The middle blob was the interference effect. And so we're able to develop this and let it evolve. The group we're working with is at the University of New South Wales, Andrea Morello's group, and they have a really good system where they're able to embed a nucleus into a silicon chip. And it's one nucleus, not an ensemble, single nucleus. They're able to control the nuclear state by first ionizing it and then applying a electric and a magnetic field, either one. And we get a nonlinear evolution. So in our case, we're working with antimony, SB in the periodic table, that's spin 7/2. If we go to bismuth, it's the highest spin in the period of the natural elements, natural stable elements, that'd be spin 9/2. So we can get up to spin 9/2 eventually. There's the ionized donor. It connects with 4 silicon, and we can control the torsion on the nucleus. The torsion on the nucleus that can be controlled by an electric field gradient gives us the IZ squared term in the Hamiltonian. So this is the same Hamiltonian that I wrote about back in 1989 in my spin system paper. We're developing a quantum control scheme for it. Essentially, this represents how we do it. So if it's spin 7/2, we have an 8-level system, and the effect of the nonlinearity is to make the levels unevenly spaced. So if we start with a coherent state in the lowest rung of the ladder, and we want to make a superposition in the lowest and highest rung, we then find a way to apply pulses that address, it's not one at a time, we apply multi-chromatic pulses that are able to drive the system to a superposition of 2 coherent states. We can do more than that, not just start here and drive to coherent states, but we can make any coherent state in this system and drive to a superposition of that coherent state and the one that has least overlap, the almost orthogonal complement. So we're able to, at least theoretically, we've shown that we're able to develop the system. This 10/J86J is the short DOI for the experimental paper from University of New South Wales that we're basing it on. So we're able to drive this particular system and make cat states. And then we claim that would be a cat state. So you can argue and say, if it spins 7 halves, that's only an 8-dimensional Hilbert space. Is it big enough to claim a cat? And for that work, so we're using a measure called, well, NR effective, but it's a form of the Fisher information. So it's a scaled Fisher information. And Dure's paper appears here, 10/F3 SMC7. And that paper uses kind of variance. So it's not a phase-based thing. It's really with respect to an observable. Normalize the Fisher information. And then if this is an order of magnitude bigger than 1, they argue, and I believe them, I mean, I'm convinced, so that becomes macroscopic. So you can see in our plot here, we have this periodic evolution into a cat and back out, into a cat and back out. We think we can do this more than 100 times. It's a very coherent evolution on the nucleus. And you can see here that, so a spin 3-half system like arsenic 75 only gets up to about 3. So we would say that's not macroscopic. Antimony 121 has spin 5 halves. That should give a macroscopic cat. Barely give a macroscopic cat. The spin 7 halves convincingly does. So we're hoping to achieve this normalized variance with respect to the Fisher information to reach 7 and claim a cat, and eventually go to bismuth 2 and do it with spin 9 halves. And that's the biggest stable element that we can find in the periodic table. So that might be the limit, but there might be other ways to do bigger spin. And then here, this is just some of the numerical simulations. We have we have some pulse sequence that we use to drive the system, and then we let it rest for the nonlinear evolution, use another pulse sequence. And as we go through this, we take a coherent state, drive it, basically rotate it on the Bloch sphere, let it go through a nonlinear evolution, and then it forms a cat state, and then we rotate to what we want. So that's how our scheme works. And that's all there is. So I'll go back to the beginning, and I'm ready for questions.